Okay, homework 2.2 is a flow through a turbine for a steam power plant. And again, this is a thermal 1 problem, adiabatic turbine with an isentropic efficiency of 80%. And we want to find out ultimately the power output of the turbine. So we'll get started with a little sketch here, the turbine. Let's draw our input, our output, and this time we know the calculated work will be positive. We're going to call this state 1 and state 2. And what I know at the inlet is the mass flow rate. The mass flow rate at the inlet has to equal the mass flow rate at the exit since it's operating in steady state. So I'm just going to write it as m dot. T1 and P1 are given. And we're going to use those values in the superheat tables to find S1 and H1. And then ultimately at the exit, what we know is m dot, of course, it's the same as the inlet. P2 is given. And we're going to find S2 from S1 because we're going to start, I'll put S2S. What we're saying here is that state 2, if we assume it's isentropic, it's not the real S2. Isentropic means that the entropy didn't change. Then we can find H2S. The subscript S is reminding us that we made an assumption that isn't exactly true in this problem, that it's isentropic. But once we find the enthalpy for the isentropic process, then we can adjust that for the adiabatic efficiency. So let's begin finding H1 and S1. If we go to the superheat tables, so at 10 MPa, which is here, and 525 degrees, we're going to have to interpolate. So it will be a little past the 3425.1. So we're going to have to take this difference, multiply that difference times 525 minus 520, and then divide that by 560 minus 520. And we'll do that here on the other page. So we've got 525 minus 520 over 560 minus 520. So we're interpolating here on the values, and we're going to take the value H2S that we're looking for here, that we're interpolating for, or rather H1 is the one we're looking for. So minus the value at 520, which is 3425.1. Divided by the value at 560, which is 3526.0 minus the value at 520 for the enthalpy, which is 3425. And so I have one equation, one unknown, and I'm fairly confident that the answer is the one shown below, 3437.71. So again, the value came from the at 520 and 10 MPa 3425.1, and at 560 3526.0. Right, so now I have H1 in kilojoule per kilogram where I had to interpolate. Now I have to do the same thing for S1. If I do that, same 525 minus 520 over 560 minus 520 equals S1 minus the S at 520 over the entropy S at 560 minus the S at 520. And when I do that with the values from that at 520, the entropy is 6.6622. At 560, 6.7864. And I can enter those values then. .6622 and 6.7864. And when I plug that in, I get S1 equals 6.6777. Okay, now I want to find H2, so if I know P2 and S2, I can then find H2S. So to do that, I'm going to go back to the tables. I'm going to look at my pressure 2, which is 0.4 bar, or 0.4 MPa rather. Let's scroll up to that value. And this is looks like not going to be in the saturation table, so let's go to the pressure tables, and we're at 0.4 bar, which is here, and we're going to compare the entropy, and it looks like our entropy is lower than the saturation value, so we're going to be in the saturating tables. If this entropy was higher than 7.67, then we would be superheated. So I'm going to use these two values and interpolate over these two values for enthalpy. So let's write those down. So let's write, for my interpolation, I'm going to have that the quality Sg minus S2S over Sg minus SF. And I put in those values at 0.4 bar, which is my pressure. So Sg is 7.67 minus my 6.6777 over 7.67 minus 1.0259. And then that same quality, so this is my quality at state 2. Of course, this is state 2s. Be the same quality, which would be Hg minus H2s over Hg minus Hf. And again, those are all at the pressure of P2, which happens to be at 0.4 bar. And when I put those values in, I get Hg at 0.4 bar is 2636.8 minus H2S over Hg, again 2636.8 minus Hf 317.58. And I put those two together, and I get that H2S is the same value I have over here, 2290.43. But that's 2S, and it's actually not isentropic. So first I find what it would be if it was isentropic, and then I use the definition of the isentropic efficiency for this turbine, which is given as 80%. And the definition would be that 80% of the maximum possible work, so the actual is going to be 80% of the ideal, and the actual would be m dot times h1 minus h2, and the ideal would be m dot h1 minus h2s. So now the m dots would cancel here, and I get that h2, just with some algebra, equals h1 minus 0.8 times h1, which was, well, I'll just write h1 minus h2s. And this, maybe, since I'm not putting in values yet, the turbine efficiency times h1 minus h2s. So now I have h1, turbine efficiency, h1, and h2s, so I can solve for h2. When I do that, I'll get 2519.89, and then finally the power output of the turbine is, this is the actual, is m dot times h1 minus h2, where I'm not using h2s, I'm using the actual h2. And when you do that, you should get 41.3. I'm not going to work out the final numbers here, but I will point out one thing, that my enthalpies are in kilojoules per kilogram. I'm trying to find mass flow right there. It is 45 kilograms per second, so let's just 45 kilograms per second times inlet enthalpy was 3437.71. Joule per kilogram minus 2519.89. So I've got the kilograms will cancel, and I'll end up with a value of kilojoules per second. So my unit, we're left with units of kilojoules per second, which is equivalent to the kilowatt, and we want the answer in megawatts, and 1 megawatt equals 1,000 kilowatts. So be careful of the units here. You're going to end up multiplying by 1 megawatt divided by, so we take our answer times 1 kilowatt over 1 kilojoule per second, because we have our, whatever our value is in kilojoules per second, and then we're going to multiply by 1 megawatt for 1,000 watts, and or kilowatts. So the kilowatts cancel, kilojoules per second cancel, and we get megawatts, so we have to divide our answer by 1,000.